The unpaid genius who saved Einstein. Imagine the year is 1915. Albert Einstein has just unveiled his revolutionary theory of general relativity, a radical new vision of gravity where massive objects warp the very fabric of space and time. But there's a problem, a potentially devastating flaw. Esteemed physicists, including Einstein's collaborator David Hilbert, are deeply troubled. The theory seems to blatantly violate one of science's most sacred principles, the conservation of energy. How can energy be conserved if gravitational energy itself creates more gravity, seemingly leading to infinite energy loops? The entire foundation of Einstein's masterpiece is wobbling. Cue an unassuming mathematician, barred from mainstream academia because of her gender and religion, working unpaid in the shadows. Her name? Emily "Emmy" Noether. Emmy Noether, born in 1882 in Germany, was a mathematical force of nature. Brilliant and tenacious, she faced a gauntlet of discrimination. After earning her PhD in mathematics in 1907, a rare feat for a woman at the time, she spent nearly a decade working unpaid at her father's university in Erlangen, often teaching under his name. Her genius, however, couldn't be ignored forever. In 1915, recognizing her unparalleled expertise in invariant theory, David Hilbert and Felix Klein brought her to the prestigious University of Göttingen. Yet, even there, prejudice prevailed. She was initially forbidden from lecturing under her own name or receiving a salary. When faculty objected to a woman joining their ranks, Hilbert famously snapped, "I do not see that the sex of the candidate is an argument against her admission. We are a university, not a bathhouse." For years, she worked invisibly, her official title non-existent, her pay non-existent. It was this unpaid, unrecognized woman who cracked the puzzle threatening Einstein's theory. In 1918, she published her monumental theorem. It wasn't just a solution, it was a fundamental revelation about the universe itself, known forever after as Noether's theorem. At its heart, the theorem establishes a breathtakingly elegant connection. For every continuous symmetry in nature, there is a corresponding conservation law. What does that mean in practice? If the laws of physics remain unchanged over time, a symmetry known as time translation invariance, then energy must be conserved. If the laws are the same no matter where you are in empty space, spatial translation symmetry, then linear momentum is conserved. Rotational symmetry? That gives us the conservation of angular momentum. Symmetry isn't just about beauty, it's the hidden architect of the universe's most fundamental rules. Noether applied this deep insight directly to Einstein's conundrum. She proved that while energy conservation might break down in a tiny localized patch of space-time warped by gravity, it holds absolutely true across the entire system. The energy wasn't vanishing, it was subtly and continuously flowing between matter and the gravitational field itself. Her rigorous mathematical framework rescued general relativity from the paradox, providing the critical validation physicists needed to accept it. Einstein himself, deeply impressed, would later call her the most significant creative mathematical genius thus far produced since the higher education of women began. Yet, despite saving his theory and revealing a cornerstone of physics, recognition and fair compensation remained elusive. She finally received a small salary in 1922 as an untenured associate professor, only to be brutally forced out by the Nazis in 1933 for being Jewish. Fleeing to the U.S., she started anew at Bryn Mawr College with Einstein's help, but tragically died just 18 months later after surgery. Her legacy? She gave physics its most powerful tool, yet physics for most of her life paid her nothing. This is the story of Emmy Noether, the genius who bound symmetry to the very laws of existence while fighting a world determined to overlook her.
The universe's hidden blueprint and a legacy denied.
Emmy Noether's sudden death in 1935 was a profound loss, cutting short a life already marked by staggering adversity. Yet, while the world of physics mourned, the monumental power of her 1918 theorem was only beginning to reveal its true scope. Noether's insight wasn't merely a clever fix for Einstein's gravitational puzzle. It was a master key unlocking the very architecture of reality, a revelation that symmetry governs the universe's deepest operating principles. Think of symmetry not just as visual balance, but as an unchanging quality under transformation. Rotate a perfect sphere. It looks identical. That rotational symmetry, Noether proved, that angular momentum, the quantity governing spinning objects from tops to planets, must be conserved. Push that sphere through empty space, where the laws of physics are identical everywhere. This spatial translation symmetry, linear momentum to be conserved, explaining why a rocket coasts effortlessly in the vacuum once thrust stops. But her genius soared higher. She showed that a symmetry hidden the fundamental equations of electromagnetism, a subtle invariance when the phase of the quantum wave function shifts globally, leads directly to the conservation of electric charge. Every electron in the cosmos possesses the same negative charge precisely because nature respects this abstract symmetry. This profound connection became the bedrock of quantum field theory, the framework describing subatomic particles and forces. The theorem's reach extended far beyond the classical world Einstein grappled with. When physicists later developed the Standard Model, the wildly successful theory explaining quarks, leptons, and the forces binding them, Noether's theorem was the indispensable scaffolding. The conservation of quantities like baryon number and lepton number arise from underlying symmetries in the quantum fields. Even the very existence of fundamental particles like the photon, the carrier of light, is tied to symmetry. The photon emerges as the necessary gauge boson, enforcing the local symmetry of electromagnetism, a concept deeply rooted in Noether's work. Attempts to unify gravity with quantum mechanics, such as string theory, continually lean on her principle, searching for the symmetries that might underpin a theory of everything. Her theorem transformed physics from a collection of observed rules into a quest for the symmetries dictating those rules. It became the physicist's Rosetta Stone, translating the language of invariance into the laws of conservation that shape everything from the spin of galaxies to the stability of atoms. Yet the bitter irony remained. While her theorem quietly revolutionized theoretical physics, becoming perhaps the most important piece of mathematical physics ever developed, Noether herself faced continued marginalization. Her belated modest salary at Göttingen ended abruptly with Nazi persecution. In exile at Bryn Mawr College, despite finding a supportive community, she was never granted the prestigious position or resources commensurate with her towering intellect. Her sudden death from complications following an ovarian cyst surgery was a devastating blow, silencing a voice that had illuminated the universe's deepest structures. Recognition came agonizingly slowly. Obituaries, including one penned by Einstein, hailed her genius, but mainstream physics history often relegated her to a footnote for decades. It took the rise of particle physics and the explicit reliance of the Standard Model on symmetry principles in the latter half of the 20th century to finally force a widespread reckoning with her indispensable contribution. Today, her theorem is foundational, taught in every advanced physics course worldwide, its name forever etched into the lexicon of science. But the reality lingers. During her most productive years, as she reshaped our understanding of existence, the establishment that benefited most profoundly from her mind offered her only prejudice, invisibility, and a lifetime of financial struggle. Emmy Noether gave physics the keys to the cosmos. The world repaid her with neglect, a stark testament to the cost of discrimination. The paradox of permanence and prejudice. Emmy Noether's untimely passing left a profound silence, but the resonance of her theorem only grew louder, echoing through the corridors of theoretical physics with increasing insistence. Yet, this burgeoning scientific permanence stood in stark, almost cruel contrast to the impermanence imposed on her life and legacy by prejudice. The years following her death saw her theorem transition from a profound insight into the indispensable cornerstone of modern physics. As physicists grappled with the bizarre new world of quantum mechanics and the forces governing elementary particles, they found Noether's connection between symmetry and conservation laws wasn't just helpful. It was utterly fundamental, the Rosetta Stone deciphering nature's deepest code. Consider a high-energy particle collision. Amidst the apparent chaos of subatomic shrapnel, physicists observe with astonishing precision that electric charge is always conserved. An electron-positron pair annihilates, the total charge before equals the charge after. This isn't coincidence. It's a direct consequence of the U-gauge symmetry of electromagnetism, a concept whose rigorous foundation stems directly from Noether. Similarly, the stability of the proton, why doesn't it simply decay into lighter particles, is intimately tied to baryon number conservation, another law arising from a deep symmetry principle illuminated by her theorem. Without this framework, understanding phenomena like neutrino oscillations or the behavior of quarks inside protons would be impossible. The Standard Model itself, describing every known fundamental force except gravity and every known particle, is constructed around the concept of local gauge symmetries. The photon, the W and Z bosons mediating the weak force, and the gluons binding quarks, all are understood as the force-carrying particles required by Noether's principle to enforce specific symmetries in the quantum fields describing matter. Her 1918 insight became the invisible scaffolding upon which the entire edifice of 20th and 21st century physics was built. The profound irony is that as Noether's theorem ascended to become perhaps the single most powerful and frequently invoked principle in theoretical physics, the memory of the woman who conceived it remained, for decades, frustratingly obscured. Recognition was a slow, grudging trickle. While Einstein's eloquent obituary declared her the most significant creative mathematical genius thus far produced since the higher education of women began, and eminent mathematicians like Hermann Weyl praised her work, institutional memory proved resistant. Textbooks summarizing breakthroughs in relativity and quantum mechanics often omitted her name, attributing the symmetry conservation link vaguely or crediting others who applied her work later. Graduate courses taught her theorem as an abstract mathematical tool, frequently divorced from the compelling story of its originator. This erasure wasn't accidental. It reflected the systemic barriers she faced throughout her career. Denied a formal position for years despite Hilbert's advocacy, paid a pittance when finally hired, excluded from academic societies, and ultimately driven from her homeland due to Nazi persecution. Her exile at Bryn Mawr, though supportive, was a fraction of the career she deserved. The scientific establishment that leaned so heavily on her intellectual framework had systematically denied her the platform, security, and recognition afforded to male colleagues of far lesser impact. Her work was universalized and absorbed, while her personhood, her struggles, and the context of her marginalization were conveniently forgotten, a process mirroring the very invisibility she experienced in life. This enduring paradox compels us to confront uncomfortable truths about the history and culture of science. Emmy Noether gave physics a unifying principle that reveals the fundamental order of the cosmos, a principle asserting that deep beneath apparent change lies profound constancy, governed by symmetry. Yet, the society and institutions of her time demonstrated a shocking lack of symmetry in their treatment of human potential, particularly regarding gender and ethnicity. The very laws she helped illuminate describe a universe governed by impartial principles, yet her own journey was warped by arbitrary prejudice. Today, while her theorem is universally lauded and her name finally adorns prestigious lectureships, institutes, and awards, her story serves as a potent, enduring reminder. It forces us to ask, how many other Emmys are we overlooking? How many revolutionary insights remain undiscovered or underdeveloped because brilliant minds face systemic barriers, whether based on gender, race, geography, or socioeconomic status? Her legacy transcends physics. It is a call to actively dismantle the barriers she faced. Celebrating her genius today necessitates not just intellectual admiration for her theorem, but a concrete commitment to ensuring that the scientific community cultivates talent with the equity and respect that was so tragically denied her. The symmetry she revealed in nature's laws stands in eternal, silent judgment against the asymmetry of the opportunities she was granted. Honoring Emmy Noether fully means building a scientific world where such profound dissonance becomes a relic of the past, ensuring that future genius, regardless of its origin, finds not neglect but the fertile ground needed to illuminate the universe's next mysteries.